So last time we ended on the local polynomial estimate. So I want to finish that discussion. And the rest of the lecture today will also be on non-parametric methods. Mainly the ideas that we'll be talking about. Mainly the reason I want to do this is because I think these ideas are very practically useful. You've seen a lot of what we've done so far has been geared towards parametric methods, right? Knowing the PDF, estimating parameters using a particular model, whether it's linear or whatever. But in practice, you'll often find that you won't have these luxuries. You won't have a PDF. You won't have a global model for the signal. And you'll be forced to do things like this. And so, in fact, if you look at the general trend in signal processing, both in 1D signal processing and in 2D signal processing, namely image processing, the trend has been that more and more stuff is using these non-parametric methods, which have been around for a long time. It's just that our field hasn't really been using them very much. So I think you'll be at a distinct advantage knowing these things, both for your research and for your future employment, let's say. Okay, so if you remember, the local polynomial estimate worked as follows. So that our signal model was yi, or the measurement, I should say, model is like this. Okay, and we just assumed the expected value of EI is 0, and the variance of EI is equal to sigma squared. But of course, remember that neither of these things means that the data has to be Gaussian distributed. Okay? So then we talked about a local expansion of this signal at some position of interest, let's say xj, which may be part of these i's or not. And we wrote this, well, let me just write the general formulation. So we minimize over a bunch of coefficients, beta 1, beta 2, the sum yi minus, and then beta 0 plus beta 1 xi minus xj, beta 2 xi minus xj squared. Okay? And this difference gets squared and it gets multiplied by k of xi xj, which is the kernel weights that we put in there. Now here, I've chosen to just do a second order approximation. Okay, so this is just happens to be a second order polynomial that I'm using. All right, so again, the unknowns are the beta 0, beta 1, and beta 2, and what we're going to do is to estimate these, and then if the only thing we're interested in is the actual value of the signal, then we just keep beta 0 and essentially discard the other two. So how does this work? Let's take all the data points that we have and we stack them into a vector. So y is going to be y1, y2, so on up to yn. Okay? And the unknowns now are in a vector, beta 0, beta 1, beta 2. Okay? And what we're going to do is we're going to write this least squares problem now in vector form as follows. So we have y minus the matrix H times beta, and I'll tell you what H is in just a second, transpose kj y minus H times beta. Okay, so we're going to minimize this over beta. And what's H? H basically captures the model here. So for beta 0, you have 1. For beta 1, you have x1 minus xj. and here you have x1 minus xj squared. Sorry, this is probably not legible. Let's see. Okay. And then so on. And then 1 xi minus xn minus xj and xn minus xj squared. Okay? Does that make sense? Okay, so again, this is just a weighted least squares problem. And so we're just going to minimize this. Just take derivatives of this with respect to beta, set it equal to 0 just as before. And what we end up with is the following. Beta hat is H transpose Aj H inverse H transpose Y. And so this is beta 0 hat, beta 1 hat, beta 2 hat. And the estimate of the signal at point xj is now beta 0 hat. It's just this first component. Okay? Now, if you are interested in the derivative of this guy, you have that too. Okay? If you're interested in the second derivative, it gives you an estimate of that as well. But you don't have to use them. Okay. Now, with this in place, let me make a couple of observations. First of all, here what we used was a polynomial expansion, right? We used a Taylor series. This doesn't have to be a Taylor series. In other words, if you are happy with another expansion, let's say you want to write a local model of the signal instead of using a Taylor series, you want to write it in terms of a wavelet expansion. That's fine too. Okay. The only condition here is that this local model has to be valid in a small neighborhood around the point of interest. Okay, so what happens if you use a different basis? So instead of here, what's the basis here? It's 1, x, x squared, and so on. It's just a standard polynomials, right? And in fact, look what happens here. The elements of that basis, evaluated for different points, make up the columns of this H. And so if you use a different basis, then all that happens is the elements of that new basis, evaluated at the proper points, get placed in the columns of this matrix. Okay. So what you can see here is that this estimate, in fact, depends very strongly on your choice of basis. Here it happens to be the polynomial. Okay. All right, so with this in place, we can also show that if you look at this expression here, this again is simply a matrix times y, right? Or sorry, it's a matrix times y. Now, if you then just take one element of this output, beta 0, which is what we have here, then what you have is just the first row of this matrix times y is going to give you beta 0, right? And so what happens is that you can write this as the sum over I of a bunch of coefficients, I'm going to call them wij times yi. Now, this is very similar to the wij that you saw me use before, except that what I'm going to do here is I'm going to put a superscript 2 because I want to denote that these are the weights that you get by using a quadratic approximation locally. Right, so before we used a constant, so I didn't have that 2 there, and I just wrote the filter like this. Okay. But what I want to get across is that these are simply, the form of the filter is exactly the same as before. It's just a linear combination of the data points that you have, except that the coefficients of the linear combination are not different from what you had before, as compared to the second order, the 0th order. It's also useful to write it this way because what you see is that, if you remember, I told you it's a very different business to just do a 0th order approximation than it is to do a second order approximation and only keep the 0th order coefficient. And you can clearly see that here. Both of them give you a filter like this, but this one has very different coefficients in front of it than what you had before. Okay? Yeah.
Which one is the better answer?
Okay, so we'll get to that in a little while. The difference is that one of them has higher variance, lower bias, and the other one the reverse. So which is better is not an easy question to answer. But there are various criteria for measuring betterness, and I will discuss them shortly. So it's useful to see kind of what these coefficients in fact look like, these coefficients. Let me show you a picture. So this is, well, in our notation, this is not P, this is little n. Okay, so this is exactly the equation I just showed you. And what I'm emphasizing here is that this, depending on what order of regression you use, right? So this is the n, that's the 0th order, first order, second order. H here is the width of the Gaussian that you use as your kernel. And you can make that width small, you can make it big. This H here is called the bandwidth.
Is this the variance?
Yes, it's the variance of the Gaussian kernel that you use. But I am purposely not calling it a variance because I don't want to confuse it with the noise variance. Okay, so that's why we call it bandwidth instead of variance. This K is the choice of the kernel. Okay, you use a Gaussian, use a Laplacian, whatever. And whatever you use, it's going to have some width, and you're going to measure that with H. And so that's the bandwidth. Okay, so it's going to look like this, and depending on whether you use 0th order, first order, or second order, this is what some of the weights are going to look like. Now, I have plotted these weights. These are actually two-dimensional data. So here we've only looked at one-dimensional data, right? So samples. So you can just completely ignore the fact that it's two-dimensional and just look across just this one line, right through the middle, okay? If you look at this, the weights that you see for the 0th order and the first order are this guy in the middle, okay? And what you notice from here is that they are right on top of each other. I'll tell you in a second why. For n equals 2, what you notice is that the shape is similar, but actually what you see is that there are negative parts to this. Okay, so this is the advantage of using higher order kernels. It allows for these weights to be something other than just a bunch of positive numbers. Okay, they still add up to 1, but they can now be negative. Now it so happens that for n equals 0 and 1, if your data is sampled uniformly, it means at equal intervals, then n equals 0 and 1 are exactly the same. The same is true for n equals 2 and 3. The same is true for every pair that are just one apart. Now, on the other hand, if you go here and just look at either this line or this line, these are the weights corresponding to this 2D data, but you can just, again, think of it as a slice here. Then, now if you look at n equals 0, n equals 1, and n equals 2, this is actually for this direction, and this is for this direction. You see that the weights are different. Okay? So when the data is not uniformly sampled, remember, you can do this regression no matter how the data is sampled. Right? That's one of the beauties of this non-parametric method, is I can just give you a bunch of scattered random data in X and Y. Okay? You can do this. So what you can see is that when the data is non-uniformly sampled, you get weights that are distinct for n equals 0, 1, and 2. And furthermore, what you notice here is that the weights are not symmetric anymore like they were here. The reason the weights are symmetric here about the origin is that the data, again, is uniformly sampled. What you see here is that these weights somehow tend to lean in one direction or another. intuitively, the reason why these weights lean in one direction or another, they lean towards the side where there's more data, okay? Which is natural, right? So it says you're going to give weight to data that is there, and when there's nothing there, then there's very little weight you need to give it. So that's this sort of biases the weights towards the density of the data that you have available. Okay? So this is just one example of what these weights look like.
Excuse me?
Yeah.
The kernel for n equal to 2 is like Mexican hat?
Well, in this case, yes. It basically, that's right. In this case, it's going to be essentially a Mexican hat, and that's what I'm about to tell you next. If you use a Gaussian kernel to start with, then the higher order kernels end up being things that are related to derivatives of the Gaussian. Okay, so that's what I was about to discuss next. Okay, so then, so as I said, this is for second order. Now let's discuss the general scenario for order P regression. And that simply means a pth order polynomial instead of a quadratic. Okay, so the formula turns out to be exactly the same. Z of xj equals sum over I, wij p of yi. Again, a linear combination, except that these coefficients are different. Now, it turns out that I'm not going to prove it to you, but the coefficients wij of order p are basically k xi xj times pi xj, where these pi's turn out to be polynomials. And here's what they are. So pi xj is alpha 0 plus alpha 1 x1 minus xj plus, or xi minus xj plus alpha 2 xi minus xj squared, and so on, plus alpha p xi minus xj to the p. Okay? So basically you start with a Gaussian kernel, or whatever kernel, and the pth order turns out to be this, the polynomial multiplied by the kernel. Now when you have a Gaussian, it's, you have e to the minus x squared, right? So when you differentiate a Gaussian, what happens is you get an x in front of it, then you get an x squared in front of it, and an x cubed in front of it, so you see exactly how this comes out. Okay?
This is just for Gaussian kernel?
No, this is actually true for a general kernel. But the polynomials, the coefficients in front of these polynomials will be different depending on what kernel you use. Okay? So remember, the kernel is separate than the order of the regression, right? So if you do polynomial regression, then whatever kernel you use, this will work for it. Okay? But it's just easy to see the example of the Gaussian giving you this data. The proof in the general case is much more complicated. Okay. And of course, as you can see clearly here, is if we started with a kernel that was all positive numbers, now you have a polynomial multiplying it. Therefore, these weights are no longer positive. Okay? And that becomes very clear once you look at this polynomial, because the sign of this polynomial is going to depend on these coefficients. Okay? So these are no longer necessarily bigger than or equal to 0. Okay, so we started off with a weighted least squares formulation with the weights given by these k's, and we ended up with a formula like this, which is very nice, simple, convenient. But what about the performance? How well is this thing going to perform? Well, the coefficients and the estimation procedure is optimal in the sense of weighted least squares, right? Because that's how we minimize the coefficients. But then we might want to know, okay, it's optimal in the weighted least square sense, but how about mean squared error? What's the mean squared error of this estimate? And we can calculate that. What about performance in terms of mean squared error? So let me go to another page. Okay, so z hat xj sum Wij times yi. Okay, so the first thing we do if we want to measure mean squared error is you compute the bias and you compute the variance of this estimate. Now here, the bias and the variance are going to be computed point-wise, right? So first, let's take a look at the expected value of z hat xj. This turns out to be sum over I wij p z of xi. Okay? That's not hard to see because y is z of xi plus noise. Noise is zero mean, so this becomes the expected value of the estimate at that point. Okay? And the variance, z hat xj, this is sigma squared times the sum, again over I, 1 to n, of wij p, these coefficients squared. Okay. So then if we look at the mean squared error, at a particular position, say xj, this is sigma squared times the sum, wijp squared, plus sum over I, or I, wijp z xi. Okay, so this is, sorry, this thing has to be squared. Let's see. Nope, sorry. So this is the expected value. So the bias is going to be the coefficients here are going to be subtracting 1 from them, right? So the bias is going to be z. It's going to be z hat, z minus z hat, right? So we're going to subtract 1 from these coefficients, and it's going to be the sum over I of wij p minus 1 of xi squared. Okay. Okay, so a couple of things worth pointing out is that obviously you can see, so this, and this is the variance, obviously you can see that the variance here doesn't depend on the underlying signal that you don't know. But the bias always does. So in other words, whatever estimation procedure you use here, no matter what the order is, whatever kernel you use, you can always characterize the variance of the estimate. That's easy to do. You don't need to know the underlying signal to do that. But in order to understand the bias, you need to know something about the underlying signal. And that's usually the case, right? Whenever you compute estimators, the variance is easy to characterize, the bias is hard to characterize. And also you can see that the variance and bias, the balance between these two, is directly related, in either case, to the order of the regression that you use, and implicitly, the choice of k, which in this case is a Gaussian, is inside the w's, right? So that also turns out to affect the order of, the balance between the bias and the variance. So what happens, for instance, is that as far as regression order is concerned, smaller p, smaller regression order, means that what you have is a smaller variance, larger bias. And larger p, the reverse. Okay? Larger variance and lower bias. And this is intuitively not hard to see because larger p means you have more terms in that local approximation. So what you're doing is you're allowing the curve more room to move around in every point where you're estimating. So you would expect naturally your curve to be having more variance at any given point. And that's what this means. What you don't see in here is the effect of the bandwidth. The effect of the bandwidth is inside these W's. We'll talk about that a little bit later. But basically what happens is that if the bandwidth is large, what you get is a smoother curve. Okay? Which means smaller variance and larger bias, and vice versa. So this would be larger bandwidth and smaller. Okay? Does that make sense? Okay, so now that we've talked about the general polynomial formulation, let me go back for a little while to the zeroth order regression. I may have given you the impression that somehow the zeroth order regression is too limited to do anything because it's zeroth order. In other words, because these coefficients are always positive, that you have a problem. Well, you do have a problem to the extent that, the number of degrees of freedom is limited. Okay? But even in that case, remember you still have the bandwidth you can play with. You still have the choice of the kernel to play with. So it's not like for the zeroth order regression, the balance between the bias and the variance is some fixed thing. You can still play with it. And so in that case, it's actually a lot easier to analyze how you trade off the bias and the variance. And so that's what I want to talk about, because I think it builds on a lot of things that we've studied so far, and it'll be kind of rewarding to see at the end how everything gets put together. So let's go back and talk about regression. Again, this is zeroth order in matrix form. And all I mean is I'm going to write everything using matrix notation. So let's say z hat of xj, this is the sum wij yi over I, and I'm not putting any superscript here because I'm doing zeroth order. So I'm going to write this as a vector, wj transpose times y, where y is y1 through yn. And now what I'm going to do is I'm going to take all the values of z hat that I've estimated at all the points, and I'm going to stack them into a vector. So z hat, this is going to be z hat x1, z hat x2, z hat xn. Okay. One thing I want to warn you about is that the x's that I'm putting in here are positions where I actually have data points. So for the time being, for the purposes of the present discussion, I'm not going to deal with the case where I'm going to estimate a position where there was no data point. Okay? So what this is, you can think of this purely as a denoising problem. In other words, you're given a sequence of noisy y's, and all you want to do is come up with a clean sequence of z's at the same positions. Okay? So if you write this in this fashion, then what you can write is each one of these w's can be put in a row of a vector, row of a matrix. So W1 transpose, W2 transpose, and so on. Wn transpose. The whole thing times y. Okay? So now this we can call W. Just some big matrix W, the rows of which are these guys. Okay, so let's rewrite the whole thing. And z hat equals W y. And so this is n by 1, this is n by n, and this is n by 1. Okay? So by virtue of the fact that I'm only treating the data points that are already there, this matrix W is a square matrix. I can do the same analysis if W is not square. The only difference is that I would have to use singular value decomposition instead of eigenvalue decomposition. But let's just stick with this. Okay. So now this matrix W is an n by n matrix, which turns out to have some very interesting and special properties. It's not just some run-of-the-mill matrix. So properties of W. Well, first of all, each element is positive. We already know that. We're doing zeroth order. We're picking a kernel that's positive. So Wij is strictly bigger than 0. Second property is that each row sums to 1. Right? Each row of this matrix sums to 1 because that's how we made the weights. We normalized them so that they would sum to 1, by definition. Another way to write this is W times a vector of 1s is equal to the vector of 1s. Okay? And if you look at this, what this immediately tells you is that W has an eigenvalue equal to 1. Right? And furthermore, the eigenvector corresponding to that eigenvalue is a constant vector. Right? So these are just from very simple observations, you're now beginning to see some nice properties follow. Okay, so let me write this down. Lambda, the largest eigenvalue is 1. Let me call this lambda 1. And the eigenvector corresponding to that, V1, is constant. But generally, we normalize eigenvectors so that they have length 1, right? So what I'm going to do is multiply this by 1 over square root of n so that its length is equal to 1. And if you remember, if a vector is an eigenvector, then any constant multiple of it is still an eigenvector. So this is okay. Okay. The other thing is that W is positive definite. And so what that means is that the eigenvalues are all bigger than or equal to 0. Or at least the real part is bigger than or equal to 0. Okay? Now I haven't proved this to you, but it turns out that if you pick a kernel, K, which is positive definite, in other words, it has positive values all the time, and it's symmetric, then the corresponding W is guaranteed to be positive definite as well. Okay, another thing to point out is that the limit, as k goes to infinity, of W to the k, what do you think is going to happen to W if you raise it to the kth power? Close.
Close.
What happens is that you don't actually get an identity. You get a matrix which has constant rows. you get a rank 1 matrix. Okay? What ends up happening, in fact, is that the eigenvalues of this guy, the largest eigenvalue is 1, and all the other eigenvalues are less than 1, but positive. So what ends up happening is that if you raise a matrix to the kth power, what happens to its eigenvalues? They get raised to that power, right? So think of the lambda as the eigenvalue. Lambda to the k, if you're talking about the first one, doesn't change. It stays what it is. All the other eigenvalues get pushed down to 0, right? So at the end, when you raise w to the kth power, you have just one eigenvector left over and one eigenvalue with it, right? And it turns out that gives you a rank 1 matrix. In fact, that rank 1 matrix is exactly 1 times U1 transpose, where this U1 is a so-called left eigenvector. It's the dominant left eigenvector of this matrix W. Okay? And in fact, remember, one of the other properties that this is going to have is that because W has rows that sum up to 1, any power of W is going to have rows that sum up to 1. Right? Is that clear? Because if rows summing up to 1 means what? It means W times 1 is equal to 1, right? The vector of 1. So now if you say W times 1, what's that? That's W times 1, which is 1 again. Okay? So this thing sums up to 1, which means that the sum of the elements in U1 also have to sum up to 1. So the bottom line is if you raise W to the kth power, you get a matrix of rank 1, described exactly by this, which has constant rows, and those constant rows add up to 1. Okay? So from this very simple construction, we got this really interesting W. Okay? So now from this very interesting W, we can gain a lot of insight. You had a question?
How did you know that the maximum eigenvalue is 1?
This is from a very famous and well-studied theory called, well, there's a theorem called the Perron-Frobenius theorem for positive matrices. What the theorem says is that if you have a positive matrix, if you have a matrix with all positive elements, and it satisfies this property, its rows sum up to 1, then its spectrum is contained in the interval 0 to 1. And the largest eigenvalue is 1, and all the other ones are below it. Okay? So, if you want to read more about it, this is probably one of the most famous results in all of algebra in the 19th century. Okay. These matrices, by the way, whose rows sum up to 1, there's a name for them. They are called stochastic matrices. Sometimes they're also called Markov matrices. So if you look in the literature, you'll see both of those names used. Okay, so one thing that we didn't talk about is whether W is in fact a symmetric matrix or not. It turns out that generally speaking, W is not symmetric, the way we've described it. Okay? And that's not very difficult to see. So W is generally not symmetric. But let me just point out something. Everything that I just showed you here was that these eigenvalues were positive, and I said the matrix is positive definite, right? But I'm saying it's not symmetric. So one of the interesting things about this matrix W is that in general, we always talk about matrices being symmetric positive definite. Right? Most people think that they're the same thing. I mean, if you're positive definite, you must be symmetric. Here's an example where that's not the case. Okay, so you can have a matrix that is positive definite, but it doesn't have to be symmetric. Now, how do you know that it's not symmetric? I mean, let me kind of give you the punchline. We're going to assume that it's symmetric because it's very, very close to being symmetric. But here's a quick demonstration that it is not symmetric. Okay? So take the matrix Kij, okay, which is it has elements k of xi, xj. Right? Okay. Now take these and put them into matrix form, so you have a matrix K now with these elements in it. Okay, the matrix W turns out to be D inverse times K, where D is simply, or I should say DII for every I. It's a diagonal matrix with the sum of k, xi, xj over I. Okay? Why is that? Because wij is kij divided by sum kij over I. This was the definition of W. So if K is a matrix with these elements and D is a diagonal matrix where the diagonal elements are these normalization factors, then obviously D inverse K is going to give me exactly the matrix W, right? Now, you know that K is symmetric, right? Because K, Xi, Xj is symmetric. It's a Gaussian, right? If you flip Xi and Xj, nothing happens. But when you multiply a symmetric matrix by a diagonal, which does not have constant values along the diagonal, you don't get a symmetric matrix back, right? That's pretty obvious. So this W is generally not symmetric. However, it turns out that this D, the elements along the diagonal of D are not that different from each other, okay? So when you normalize, even though technically speaking you don't get exactly a symmetric matrix W, you get something awfully close. And there are technical results, which I'm not going to show you, about how close they are. But trust me, they're close enough that we can just assume W is symmetric and move on. Okay? And that's what I'm going to do. So we're going to assume W is symmetric. By the way, assuming that W is symmetric implies one more thing, which we didn't have before, which is that not only do the rows sum up to 1, the columns also now sum up to 1 because of the symmetry. And so what this means is that W is now called doubly stochastic or doubly Markov. Okay? And there's a huge amount of literature about both stochastic matrices and doubly stochastic matrices. Okay, so now if W is symmetric, what I can do now is I can write an eigendecomposition for W as follows. I can write W equals V S V transpose. Remember, if W was not symmetric, then I would have to write V S V inverse. Okay? But because W is symmetric now by assumption, V is now an orthonormal matrix. So V transpose V is V V transpose equals identity. Okay. All right, now with this setup in place, I can now study the performance of the filter with this matrix formulation in a lot more clean and tidy way. So let me just remind you, again, in vector form, y is equal to z plus e. Okay? And what we're going to do is z hat is equal to w times y. This is the estimate. This is the non-parametric estimate of the signal given the noisy measurements y. So now, the expected value of z hat is equal to w times the expected value of y, which is w times z. Right? Okay, similarly, so if this is the expected value, then the bias is going to be WZ minus Z, which is W minus identity times Z. Right? Okay. So now let's find the covariance. Covariance of Z hat is W, covariance of Y, W transpose. And I'm going to assume here that expected value of E is 0 and covariance of E is sigma squared identity. Okay? Again, not Gaussian, but just the mean and the variance. Okay, so then this becomes sigma squared W transpose. Okay? So now if I use the eigendecomposition for W in here, what I get is the covariance is sigma squared V S V transpose times V S V transpose. And this is identity, so this becomes sigma squared V S squared V transpose. Okay? All right, so now I have the bias and I have the variance, or the covariance, and I can write down now the mean squared error, just like before. This is a vector parameter that we're estimating, this Z. So the mean squared error, the scalar mean squared error, is the norm of the bias squared plus the trace of the covariance matrix. Okay, this is just from long ago when we did the analysis of the mean squared error. So bias is the norm of W minus I Z squared, and the covariance is sigma squared. What's the trace of the covariance matrix? This is the covariance matrix, right? What's the trace of this matrix? Let me remind you what the definition of the trace is. It's either the sum of the diagonal elements or it's the sum of the eigenvalues. The same thing. Okay, the trace is the sum of the eigenvalues. So what are the eigenvalues of this matrix? They are the square of the eigenvalues of W, right? So this term here simply becomes the sum, I equals 1 to n, lambda I squared. Okay? Make sense? All right, so again, the bias term depends on the signal, the variance term does not. All right, what do we do with this next? What I'm going to do is I want to understand how this mean squared error behaves depending on Z and depending on lambda and so on. So what I'm going to do is I'm going to consider Z, it's a vector of length n, right? I'm going to consider it as being written in the basis, which is the columns of V. Okay? V has n columns. They are orthonormal vectors, and therefore they span the n-dimensional Euclidean space. Z is just a vector in that space. So I'm going to write Z as a linear combination of those vectors. So I'm going to write Z as some linear combination, let me call it B0I VI, I equals 1 to n. Or written in a more tidy way, I'm going to write this as V times B0, where B0 is B01, B02, and so on. Okay? As a matter of fact, this is not a terribly unfamiliar thing to do. The vectors V, you can think of them as basically the Fourier basis, right? The Fourier basis is an orthonormal basis, right? So this is basically the discrete Fourier transform that you're looking at. These VI's are the columns that you get from a DFT matrix. So all we're saying is, what are the components of the signal at various frequencies? And the frequencies here are measured, or they're indexed by I. Right? So these are the spectral components of this Z in that basis. Okay, so these are, let me just Fourier coefficients. I'll put it in quotes because it's it's an intuitive tool here we're using. It's an intuition. Okay, so with this in place, I can actually simplify this term a little bit, or actually a lot. Let me show you how. So W minus I times Z norm squared is norm. Okay, W is VS V transpose, right? I'm just substituting that. Instead of identity, I'm going to write V V transpose. Okay? And instead of Z, I'm going to write V V0. Okay? Now what happens is this term becomes norm V S minus I V transpose V V0 norm squared. This is identity. So this is norm V S minus I V0 squared. Okay? Now one more step. This is in fact equal to the norm of S minus I V0 squared. Why? Because V is an orthonormal matrix. Okay? What's an example intuitively an orthonormal matrix? A rotation. Okay? So all this is doing is S minus I times V0 is a vector. V is simply rotating it in this n-dimensional space. Therefore, it's not changing its magnitude. This is the 2 norm. This is the L2 norm. And V is an orthogonal matrix. This is called the orthogonal invariance of the L2 norm. So if you take a vector and multiply it by an orthogonal matrix, its length doesn't change. And that's what I've used to get to this last point. Okay, is that clear? So this is kind of a big leap now. Okay, so now we take this, and what does this mean in terms of this bias? What it means is that now the norm of the bias squared, which is norm S minus I A0 squared, can be written as the sum over I of lambda I minus 1 squared V0 I squared. Okay? I can write all of this now in terms of the eigenvalues. So now I have this wonderfully simple expression for the mean squared error. It's the sum I equals 1 to n lambda I minus 1 squared V0 I squared plus sigma squared sum I equals 1 to n lambda I squared. So this is the variance, and this is the bias squared. Okay? So what have I done so far? What we've done is we have started with a kernel, K. We've set up a weighted least squares problem. We've solved it. And we've gotten an estimate, Z hat, which can be written as W times Y. Right? Then we've studied the performance of that estimator and come up with the following expression for the mean squared error. In other words, when I started off and I wrote down that weighted least squares problem, I really had no idea how the mean squared error was going to behave, right? Now I have some idea how it's going to behave. Okay. So looking at this, one very natural and sort of obvious question that comes to mind is, if I look at this equation, what would be the best eigenvalues for W in order for this mean squared error to be as small as possible. Okay? It's a perfectly reasonable question to ask. So let's ask it. How should lambda I be chosen? So what sequence of lambda i's gives the lowest mean squared error? Okay? What we're going to do is take the derivative and set it equal to 0 with respect to lambda I, right? Now the beauty of this is that this derivative is really easy, right? This is just a quadratic in terms of the lambda I. So if I take this derivative, what I get is 2 times lambda I minus 1 b0I squared plus 2 sigma squared lambda I. Okay? And you solve this. And here's what you get. Lambda I star, this is the optimal spectrum for W, is b0I squared divided by b0I squared plus sigma squared. And what does this look like? Let me write it a different way. This is 1 over 1 plus p0I squared over sigma squared to the minus 1. Familiar? Signal to noise ratio, right? 1 over 1 plus signal to noise ratio to the minus 1, which is exactly the Wiener filter. Okay? So this is 1 over 1 plus SNR I to the minus 1. And SNR I is what? Remember the interpretation that I gave you for B0I. B0I squared is the energy of the signal in the ith frequency component, in the ith spectral component. And this is the variance of the noise. So this is the SNR in the ith frequency channel. Okay? And for those of you who are communications people, this is, we're breaking up into channels here. I is indexing the channel. This is the SNR in the ith channel. Okay? So what this says is that the filter that works the best, which minimizes the mean squared error, is the one that, in fact, gives you lambda i's spectra that are given by this Wiener filter condition. So, I started with weighted least squares, and I ended up with this as my optimal estimate, right? So now you can ask various questions. Can I guarantee that somehow the choice of the kernel will lead me to this best estimate? Okay. The answer is not known. Okay? In general, the answer is no. Because if let's say you pick a Gaussian kernel at the beginning, and you end up with some lambda i's, right? Those lambda i's won't satisfy this condition. And the reason they won't satisfy this condition, because those lambda i's don't know anything about B, right? So there's no way you could have predicted what lambdas you would get, which would be the optimal ones. One other thing you could do is somehow guess what these numbers are. Okay? So this is related to what we talked about earlier with respect to the Wiener filter. We said that the Wiener filter required you to know what? It required you to know the power spectrum of the signal, right? What's the power spectrum of the signal? It's the Fourier transform squared of its autocorrelation function, right? If the signal is not random, it's simply the Fourier transform squared, which is exactly what these components are, right? So now you can say, all right, if I have a class of signals that I'm looking at, I'm going to go make a database of signals, take all of these signals, take Fourier transforms of them, square them, okay, and use an estimate of the B0i's in order to compute a lambda I. Okay, and then I will know that my filter will have these optimality properties. Another question is, suppose you did that, right? Suppose somebody came through the door and gave you the perfect B0Is, and now you know exactly what the spectrum of W is going to be. How would you go back and figure out what kernel that corresponds to? It's not obvious, okay? That's why we always do it the other way. We start with the kernel and we end up with something. And so the struggle here is that somehow what you're going to do is you're going to try to be as smart as you can about the choice of your kernel in such a way that you will get as close to these lambda I stars as possible. This is the struggle that you go through in filtering. Without knowing the signal, you design something and you hope for the best. Okay. Now it turns out you don't have to just hope for the best. There are some very definitive methods that you can use to get to this final result. And yeah.
And the choice of the kernel would not be unique, yes.
That's right. The choice of the kernel is not unique. Now, the kernels that I've talked about so far are, we've only used the Gaussian kernel, right? But there are many, many other ones you can use. You can in fact use an exponential, right? Two double exponentials of a Laplacian kernel. You can use it.
I mean for a specific value of eigenvalues. The choice.
Oh, that's right. Yes, that's true. In other words, if you had a fixed spectrum, there may be a variety of different kernels which will end up giving you that spectrum. That's true. That may not even be the case. That's right. But the bigger picture here is that the choice of the kernels that we've made so far, whether it's Gaussian or Laplacian or square or whatever it is handicapped by the fact that it depends only on the position of the samples. Okay? In other words, the way we have chosen the kernel is so far the kernels are like this: k of xi, xj, right? And then we've set up our least squares problem, sum yi minus z xj. This is for zeroth order. Okay, k xi xj I equals 1 to n, and then we minimize over this guy, right? Now, if you look at this, what is this telling you? It's telling you the optimal spectrum depends on the underlying signal. So if you were going to take this and work your way back to designing a kernel, you wouldn't design a kernel that ignores the signal, right? This kernel ignores the signal. It's only dealing with positions of samples. It's not giving you any information about the value of those samples. But guess what? Those values contain information about the B0Is. Okay? So what you in fact want is you want to replace this with something that is not just a function of xi and xj, but also a function of yi and yj. Okay? And these are called data-dependent kernels. Okay? And I'll talk about these data-dependent kernels in the next lecture, but really the bottom line is the methods that really, really work well are not these ones, but these ones. Okay? And actually defining these is really not that hard. So for instance, one example of doing this is, remember we did k of xi, xj. This was some constant times exponential of xi minus xj squared divided by 2 sigma squared, right? Or 2h squared. Let me write h. I'm not confused with that. Okay, so it was like this. You can also define k of yi, yj as some constant times exponential minus yi minus yj squared divided by 2, let's call it h prime squared. Okay? And then you can define k of xi, xj, yi, yj as the product of these. K of xi, xj, k of yi, yj. Okay? And this turns out to be, it has a very famous name. It's called the bilateral filter. There are many, many more of these that have been defined. Okay. Bilateral filter is the simplest example. There are literally dozens of other ones that people have invented. You know, this is very simple. All you're doing is just multiplying two kernels together. They don't have to be that way. They don't have to be separable. They can be all kinds of other things as well. Okay. So we'll say a little bit more about these, and I'll show you some examples, particularly in image processing, where these things really work extremely well. But for now, let's just stick with this case where these don't depend on the signal, because the analysis is a little bit simpler. Okay? It turns out that even if they do depend on the signal, more or less the same analysis works, and you guys know about this. But for now, I don't want to confuse you with that additional layer of complication. Let's just stick with this. Okay. Okay, so then typically what we end up doing, what we do is we choose k of xi, xj, and from this we do regression, and we get z hat equals wy, and in general, lambda I for this w are not equal to the optimal ones. Okay? So, what do we do? Are we stuck? Can we continue? What's the path ahead? Do we quit? Well, it turns out there's several things you can do. A couple of them I've already mentioned. So how to improve this estimate? Well, there's several ways. Let me first show you, first mention one that we just briefly discussed. One would be to estimate the signal-to-noise ratio for each channel, for each I, and then let lambda I, so this is what you estimate, then you let lambda I be 1 over 1 plus SNR I hat to the minus 1. Okay? But if you did this, then there would be the question of what kernel does this correspond to? Right? And we don't know what kernel it corresponds to. Because if you change the eigenvalues, it's not obvious how that changes the elements of the matrix W. Right? Why is it important, by the way? I want to see if you can appreciate why it's important to know what the kernel is. Okay? What this is a very nice mathematical way of writing things down. Right? Z hat equals Wy. Very nice, very clean and tight. Right? But imagine if Y was length 1 million. Okay? Then the matrix W would be 1 million by 1 million. Right? You don't want to do filtering like this. What you want to do is to come up with a kernel that's going to do moving least squares. Okay? Which is all a bunch of very simple operations. Right? The sum of a coefficient times yi's. That's what you want to do. That's the simple thing to do. So it's okay to say, well, I'm going to do this, but then you should be able to somehow go back from this to the kernel so that you can efficiently implement the algorithm in practice. And doing this makes it hard. Okay? Especially at very long signals. Okay, so another option, so then the question is, what kernel? And we don't know the answer. Another way of doing this is you might estimate the signal-to-noise ratio like this. By the way, when I say estimate the signal-to-noise ratio, you can use any of the estimation procedures that you've learned so far. Okay, if you have a statistical model, use maximum likelihood. If you have a prior, use MAP. Use minimum mean squared error, Bayesian minimum mean squared error. Any of the methods that you've learned so far can be used to estimate this SNR. Okay, so you estimate SNR, but you stick to the kernel that you have. Okay? Let's say the kernel is the Gaussian, xi, xj, some constant, exponential minus xi minus xj squared divided by 2h squared. Okay? So remember, k gave us the matrix K, this gave us the matrix W, which gave us the eigenvalues, right? So, from this, I can say lambda I, the best lambda I is going to be approximately 1 over 1 plus SNR I hat to the minus 1. Now what I can do is I can go in the forward direction. I can take this bandwidth and I can keep turning the bandwidth up and down and watching what happens to the eigenvalues until I get eigenvalues that are close to that. Do you see what the difference is here? In other words, this first one was like, whoa, I'm going to have to go back and design a whole new kernel. This one says, don't design a whole new kernel. You have a parameter you can play with. So just adjust that parameter so that you get as close to this as possible, as close to the Wiener condition as possible. Okay? And this is one way of adjusting the bandwidth. This is one way of optimizing the bandwidth. Okay, so that's the second one. These are both very practical. I mean, this is much more practical than that one. And people use these things, well, this one in particular. So the third method is something that has an unexpected behavior, which you wouldn't expect from just taking the filter and doing what it's suggested to do, which is apply it multiple times. Okay. So you design this filter W, and you apply it to Y just once, and you get Z hat, and you throw arms up, and you say, done. Okay. So now you might ask, I've worked really hard to design this W. What if I just apply it again? Right? So instead of W times Y, I do W squared times Y. I do W cubed times Y, and so on. Well, if I keep this up forever, eventually what I'm going to get is something useless. Right? Because what this is going to do is it's going to keep averaging the data until at the end, I'm going to get a constant signal back. Right? Nothing terribly interesting. But somewhere between this and that constant signal, something interesting happens. Okay. So the third option is iterative application of W. And what I mean by that is you construct an iteration like this, W times zk minus 1. This is not that different from iterations that we've seen before. The equivalent way of writing this is z hat k equals W to the k times Y. Okay? All right, so first of all, remember that W to the k, the limit as k goes to infinity of W to the k, is 1 times U1 transpose, where U1 is a fixed vector which sums up to 1, right? So the limit as k goes to infinity of z hat k is the limit as k goes to infinity of 1 times U1 transpose Y. This is, sorry, there's no limit anymore. Okay? U1 transpose Y is a single number, right? So this is just a constant. Okay? So this is a vector of constants. Constant, constant, and so on. Constant, same constant. Okay? So in other words, if you apply this infinitely many times, what you end up with is a constant signal. So let's see what happens in between. So W to the k is Vs V transpose to the kth power. And this is Vs to the k V transpose. And so the eigenvalues of this guy are now going to be lambda I to the k, right? eigenvalues were lambda, now the eigenvalues are lambda to the k. So now I can write down the mean squared error for this case as a function of the iterations k. So the mean squared error as a function of k is the sum I equals 1 to n. It's exactly the same form as before, except for the fact that, let me go back to this and show you what it looked like. Okay, so here, what did we have before? We had lambda I minus 1 squared, and then sigma squared lambda I squared, right? So all I have to do is I'm going to replace lambda I with lambda I to the k. Make sense? That's it. Okay, so this becomes lambda I to the k minus 1 squared be 0I squared plus sigma squared lambda I to the 2k. Okay, so the sum actually applies to the whole thing. Okay? Now something very interesting happens here. Remember, this part corresponds to the bias, and this part corresponds to the variance, right? Take a look at what happens as you increase k. As you increase k, this term gets smaller and smaller. Because remember, the lambdas are less than 1, right? So this term actually goes to 0. Whereas this term, lambda I, again less than 1, lambda I minus 1 squared, this gets bigger. It gets closer and closer to 1. So the bias goes up. Okay. And intuitively, again, this makes sense because what did we just say? We said as you keep doing this, you get a constant signal back. A constant signal has variance 0. Okay, which corresponds to this term dying out. But that constant signal has a horribly ugly estimate, right? So remember, in the first midterm, we did a practice question about can you come up with an estimate that has 0 variance? And I think everybody said no. Yes, you can. Come up with constant, right? The price you pay is that you have ugly bias, and this is the ugly bias that you end up with. Okay. So the point is, what you observe now is that what's happened is by simply taking the matrix W and applying it to the same signal again and again and again, you are implicitly changing the balance between the bias and the variance. And if your objective is to somehow make the mean squared error smaller, then maybe in the process of increasing the bias and reducing the variance, you will hit a smaller mean squared error. Okay? There's no guarantee that will happen. I'll show you what the condition is for this to happen, and it's very interesting. But it is possible that that may happen. Okay? So let's take a look and see whether, in fact, this iteration will improve the mean squared error. Okay, so first of all, how can we know that this iteration improves the mean squared error? Yeah?
W is a matrix which denoises the signal, yes?
Mm-hmm.
So if we apply this matrix many times, we expect the signal to be completely denoised. And we explain.
No, what happens is that the signal, if you apply W once, because W is not doing a perfect job, what it does is not only does it attempt to get rid of noise, but also, because it doesn't do a perfect job, it also removes part of the signal. And the problem with applying it again is that the filter is equally stupid as it was the last time. It says, oh, another signal to denoise, so it removes more of the signal. And if you keep doing that, ultimately it removes all the signal. And the only thing that's left is a constant. Does that make sense?
So this constant is not a denoised version of this?
No, it is not a denoised version. It is a version of the signal that has been killed. Okay? The only thing that's left of it is a DC. Okay? Now, if that's what you want, maybe that last bit is useful to you. But in general, that last constant is not I mean, let's say the signal is a picture of somebody's face, right? And if you keep doing it, you get a constant. That's not a face anymore. Not useful. By the way, I should also mention that this whole process of taking a signal and this whole process of applying the filter again and again, this is called diffusion. Okay, so I should put that here. Okay, let me explain why it's called diffusion. It turns out that this is a discrete equation, right? It's indexed by a discrete variable k. If you wrote this filtering framework, I've done everything with matrices here. If you did this whole filtering framework in the continuous domain, in continuous time, this iteration would correspond exactly to the heat equation. Okay? And the heat equation, as you might remember, basically is a partial differential equation that tells you how heat propagates through a medium. Okay? As an example, let's say you have a piece of metal, and at one end of this piece of metal you put a heat source. Okay? What happens after a while? This heat propagates until the whole piece of metal is at the same temperature. Right? That's the steady state result. That whole piece of metal being at the same temperature is this constant signal. Okay? So that's exactly what this framework is doing. If you're interested in more details about how this is diffusion and how the physics sort of enters into this, I'll be happy to point you to references. But it's intuitively, it makes sense, right? I mean, you're doing the same thing over and over again, which exactly is exactly what the diffusion equation does. Kind of, you propagate the heat a little bit, you propagate a little bit more, until everything's at the same temperature.
Excuse me?
Yeah.
May you go to the previous page?
Sure. This one?
Yep. The last thing, Z ka equal to WZ ka minus 1.
Yeah, this
It's
one?
not same as, yeah.
Mm-hmm.
If in each iteration I'm updating W,
Mm-hmm.
it's not same as the Z ka equal
That's right.
to W
That's right.
to the power of. Yeah.
Exactly. So you have a couple of choices here. What I described here is a standard diffusion, which means that you compute the weights W from the original noisy data. Okay? And then you apply it again and again. You can also do what you suggested, which is you take the signal, you apply W to it, you compute W, you apply W to it, and then you compute the W again, not from the original data, but from the new data. Now, that makes a difference if your W, in fact, depends on the data. Right? So that goes back one more slide here. But if your W does not depend on the data, then it's exactly the same. Okay.
In this case, when we apply different W's, we finally reach to the completely denoised signal.
You still don't reach a completely denoised signal.
Because
No.
because in each step we are updating the W matrix.
Well, okay, so think about what the W matrix is, right? Even if you do that at each stage, the W matrix still has eigenvalues that are between 0 and 1, right? So what I said here was W to the K has eigenvalues that die out, right? The eigenvalues of the product of a bunch of different W's still decay to 0. Okay? So you get the same behavior. Asymptotically, you get the same behavior. You get a constant signal back. Maybe a different constant signal, but you get a constant signal back. Okay? So because instead of lambda I to the K, you get lambda I1, lambda I2, lambda I3, each one of them from a different ratio, but all of those still, less than 1, they still die out. Okay? So I think from your questions, what you're saying is, can we come up with an iteration that does not give you a constant signal? And the answer is yes. And that iteration is something I don't have time to get into this time, or we'll talk about it next time. Okay? That iteration is completely different from diffusion. That is something else called reaction diffusion equation. Okay? So a reaction diffusion is something where the heat is not just simply propagating, but somewhere along this metal bar, there are also points where cold is being introduced. Okay? And it turns out the way we introduce that cold is we take the signal that has been denoised and we compare it to the original noisy signal. Okay? If you've done a perfect job, then that difference should look like pure noise. Right? I mean, you give me a noisy signal, I give you a denoised version back. Look at the difference. It's called the residual. If that residual looks perfectly random, then you've done a great job. However, if that residual doesn't look perfectly random, then what I want to do is filter the residual to get back some of the signal that the filter accidentally took out. And I want to add that bit that I took back into my estimate. And this gives you those little pieces of cold that react against the diffusion. And you get a very different steady state solution. Okay, so we'll talk about that next time. So we'll do two things. One of them is talk about that, and the second thing is, before that, I want to describe what are the conditions about which you can guarantee that this iteration in fact improves the mean squared error, and when do you reach the minimum mean squared error. Okay, it turns out, guess what? You reach the minimum mean squared error after a certain number of iterations where the eigenvalues are as close as they're going to get to the Wiener filter. And of course, because here you do not have a continuous parameter that you're adjusting. You know, you go from k from 1 to 2 to 3 to 4. At k equals 10, you might be above the error that Wiener filter gives you. At k equals 11, you might be above it again. So you might have reached the minimum somewhere between, but because your iterations are discrete, you might just skip over that minimum mean squared error. So there's no guarantee you actually hit it exactly, because k is a discrete variable. But anyway, we'll see more of that next time. Okay? All right. Any other questions? All right. So your graded homeworks are here. Please make sure to pick them up. Oh, by the way, I'm planning on finding some time to scan all of these notes and putting them on the web page, so that then if you want to go back and look at the lectures, you'll have the same notes, because I don't always exactly say the same thing that's in the notes that are already there. So so keep looking on the course web page. Hopefully by the time we get around to studying for the final, I will have them all scanned and put up. Okay?
Does the material for the midterm comes on the final also?
Yes, yes. It's a comprehensive final. Everything.